we're talking about extreme values of functions of two variables right now. Last video we were thinking about local mins and local maxes and where to find local mins and local maxes. And we know we look at critical points, which is very similar to what we had in Calculus 1. You take the derivative, you set it equal to 0, although now taking the derivative and setting it equal to 0 means taking the partial derivatives with respect to both x and y and setting them equal to 0. So let's draw a couple pictures here. So, we might have some kind of hill here. And so at the top of this hill, this would be a local max. And if you think about it, the tangent plane to the top of the hill would be a flat plane. And that would correspond to the partial derivatives being 0. We also might have a local min that could look something like this, the bottom of a valley. So down here, we'd have a local minimum. And again, the tangent plane would be tangent flat under that valley. The partial derivatives are both 0. Are there any other possibilities? And so the answer is yes. So I'm asking that question. The answer is probably yes. Well, let's take a look here at this definition. A differentiable function f of xy has a saddle point at a critical point AB. If in every open disk centered at AB, there are domain points xy with f of xy is bigger than f of AB, and domain points xy with f of y is strictly less than f of AB. So what is a saddle point? Saddle point is a critical point, so it must be a critical point. The partial derivatives must be 0, but it's neither a local min nor a local max. There are some nearby points that the function is greater than the value of the function at AB. Some nearby points f of xy, nearby points xy where f of xy is less than f of AB. And I should say, we would call a specific point AB, comma f of AB on the graph. This is a saddle point of the surface. Okay, so now we should be thinking about what is a saddle point? Why do we call a saddle point? What does it look like? And so this is where I want to get out a very classic tool to help illustrate saddle points, which is this Pringles potato chip. So Pringles potato chip has a very unique shape here. And first off, realize that this does look, the potato chip here looks kind of like a horse's saddle. So like if my finger here is the back of the horse, okay, the saddle sits along the back of the horse. And so the thing that I want us to realize is that at this point right here, yeah, that's actually working. That purple point is actually a saddle point where the chip is assumed that we're thinking about the chip as being the surface of our function. First off, let's think about what happens if we slice the chip this way. So we slice the chip this way. We see that if you go along from this chip in this direction, you go down. You go from this chip in this spot here and go over this way, you also go down. But at the very point where we're at this saddle point, the partial derivative here is 0. So slicing it this way, it looks like that this point right here is a local maximum. However, if I take a different marker here, is this pink one working? Yeah. So what happens if we slice it going the other way here? And we slice it going in the other way. Well, starting right here and moving in this direction, we go up. Starting right here and moving in this direction, we go up. And so the partial derivative moving in this direction is going to be 0. We're bottoming out there. But if slicing it in this way, it looks like this point here is a local minimum. So we slice it like this. Along this pink line, it looks like we have a local minimum. If we slice it like this along the purple line, it looks like it's a local maximum. And so this is exactly an example of a saddle point. So first off, the partial derivatives at this point are both 0. You know, it's flat there and flat there. You know, the tangent plane at that point would be exactly would be completely flat. But then in one direction it looks like a local minimum, in one direction it looks like a local maximum. Now you can have more complicated saddle points than just this one, but this is showing you, well, if you go a little bit in this direction, you're going to be higher than the saddle point. So that's corresponding to if you go in this direction, f of xy is a little bit bigger than f of ab. But if you move in the purple direction, f of xy, you're always going to be a little bit less than f of ab. And so this is showing us, let me draw, let's see, I can do the drawing here. This is often what a drawing of the saddle point is going to look like, because in one direction it looks like a local max, in one direction it looks like a local minimum here. Okay, so what our goal is going to be in the rest of this video, in the rest of this section, at least in the next couple of videos, is going to be to determine when, to be able to distinguish, is our critical point, is it giving a local maximum, is it going to a local minimum, or is it giving a saddle point? And we will be talking about that for the rest of this. Hopefully this picture helped illustrate what those are. Really the best examples here are the Pringle potato chips, or think about, you know, the back of a horse. In one direction you're at a local minimum, but if you're sitting here with your legs over the horse, it's a local maximum. And the chips are tasty.